Today we're going to do a simple load rundown on a basic structure where we can obviously parametrically control the size of the structure or the configuration, can change the heights and the levels, etc. And it will give us the load coming down for each column based on how many floors and where it is in the building. And a reminder that you can get more tutorials like this at our website, and you can also download the scripts if you prefer rather than building them yourself from the videos. And feel free to have a look at some of the other services we offer, including model conversion, reinforcement, visualisations, etc. Alright, for once I'm not starting with a point. I'm going to start with this rectangular grid. I thought about ways of getting this tutorial as quick as possible, and I just don't want to replicate making some basic structure over and over again, so I'm just going to set these sliders to 10,000. This is going to be the span in the X direction, and then I'll just copy and paste that into the Y direction. And then I need the number of grids in each direction, so I'm going to get another slider for that. I'll make it go up to 10, real number or integer, and the Y. Oh, there it is. Yes, it's quite tiny, so yeah, 10,000. So that's better. Now I'm going to make the span, say, I don't know, 6 meters in one direction and 5 meters in the other. I'll make it, say, 5x4 grid. Okay, so I just need a way of referencing each of these cells because it's built a polyline for each cell for me. So to do that, I'm just going to go to the curve, get the centroid, polygon center, and I'm just going to flatten that. So I've just got a list of polylines. Then I want to tag a text tag at the location of the center, and the text is going to be the number. So to get that, I just need to get the length of the list and make a series out of it. So start at 0, 1, and the count is 20, so I'll have a list of 0 to 19. I'll just turn this preview off so we can see the number. So there I can see each cell number. And what I want to do now is I want to start popping some of these up to create a basic grid building, some floors, sections. So to do that, I'm just going to use list item, and I'm going to create a list of indexes. Oops. So I'll call this level 1. I'm going to say I want number 1, 2, miss 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. I want all of these as level 1. As always, there's a lot of different ways you can do this. You can probably think of a better way than this, or a different way if you prefer, but this way works for the moment. So I'll use those indexes to grab those curves. I'll flatten that. So you can see it's grabbed all of them except 0 and 3, which I left out of my list. And then I just want to move these up. And I want to move them up by, say, 3 meters. So I'll just put 3 meters in here. Everything's in millimeters, obviously. So now we've got our level 1 structure. I'm just going to copy and paste that. Call this level 2. Then I'm going to miss out some numbers here again. Let's just go to a bit more of a plan view so I can see what I'm doing. I'm going to miss out 1 and 2. Get rid of them. I'm going to miss out 4. I'm going to miss out 8. And probably 16 as well, say. Okay, so these I'm going to move up. So I'll just copy these parts. They're the indexes I want to move up. This time I want double the height, so I'll just do an expression, x times 2. That just doubles the vector. There we go. So I've got 2 levels and they're both different. Then just to show what the structure is, I'm quickly going to put some columns in. And I'm going to do that by going to this one here, which is in the surface there's deconstruct brep, and that'll give you the properties of these squares. It'll actually make them into brep. So I've sort of skipped some steps here, like you should make those into a panel first and then deconstruct them, but this is a shortcut. So if I deconstruct that, what I really wanted out of that was the vertices, and then I want to have another move. This time I want to have a negative vector, the same vector upwards, but I want it negative, so minus x. And then I'm just going to create a line between those two. So this just joins all the corners and creates a vector, whoops, downwards. And what have I done? I haven't put in the actual points. So there you go, you've got your columns. I'm going to turn off some of these points and things just so it makes the structure clearer. So you've got your columns and your floors. And I'll just copy this and paste this in for the next set of columns. There we go. So obviously I can just choose whichever grid reference, panel reference I want to bring up to whatever floor level. I can keep going as high as we like, but to keep this demo quick, I'll just stop it there and I'll go on to the next step. Alright, so now I've got a basic structure. I want to start finding out how to get the loads, where they're going to go into the columns. So I'm just going to collect my surfaces. Now interestingly, because this component is a grid, it makes rectangles which I can just plug straight into a surface, and it will make it straight into a surface without having to use any other components, which is pretty cool. So we've got our floors. Now I want a way to work out how much of the load goes into each corner, and this is just a very simplistic method, which is actually a good method, as I'll try and explain later, but you can think of it as 1/4 goes into each column, and later we can adjust that. So to split these into quarters, these surfaces, there's a component called isotrim. Now, as always, there's a lot of ways to doing this, but this way works pretty well. It needs surfaces and it needs domain and a domain. So domains are pretty powerful. They're not the first thing you might think of using, but they're actually really useful. So I'm going to make a domain. I'm going to use the surfaces as the base, and then I'm going to split them into 2 each way. So in other words, I'm going to halve them in the X direction and the Y direction. Put that into domain, and it needs some surfaces. Now it's doing funny things, and the reason is that I've got, you can see there, I've got a list of 30 lists with 4 items each, and here I've got, or I should say 31, and I've got 31 items. So if I graph this and I turn the surfaces off, you can see that it's matched the 31 number list with the 30 list, so everything's evenly matched. So there you've got your 4 quadrants of each surface now. Right, so the next part is how do we determine where the load of each of these quadrants goes into which column. So to do that, I'm first just going to get the centroid of each quadrant. Got all the quadrants here. I've got a centroid for each one. Now I just want to relate them back to the 0Z plane, because the Z's going to confuse things. So I'm just going to deconstruct these points. And reconstruct it, but without the Z, so they'll all be at the base. Because then I can relate it to, I'm going to have everything at Z, so I can work out how it relates to the original column locations which I set up and I know from my original component. So that's nice and easy. So to do that, I'm going to use this little component here, which is pretty cool, which is closest point. There we go. So I've got all my quadrant points, and I want a list of points to search. So that's going to be all the columns. So it's going to work out what's the closest column to each of these panels. Now to do that, I've already got my points, but all I'm going to do is I'm going to sort them. So that they're in order before I start using them to index them. And then I'm just going to flatten that. Oh, sorry, I'll flatten it first. So I've just got random points in any old order, make them ordered, and then I want to get some indexes, work out some indexes for this. So again, similar to before, whoops, just going to get the length of the set. So I've got 30 items. I'm going to make a series, and the series is 0 to 29, so they're my indexes of my points. Now the next part is I'm going to use some set tools, member indexes. So member index can find items in sets. So my set is going to be the index of the closest point. Now I haven't finished this. These sort points here is what I want to search. So I've gone ahead of myself a little bit, but going back, if I put these sorted points, which is just my base points, if I preview that, you can see they're the column locations. So they're just my 30 columns, some of which aren't columns at all, but anyway, if I put that in there, turn that off for the moment, you can see what this is working out is which of the panels belong to which columns, and it gives me an index to figure that out, an index of the column location. So going back to this, I want to find which column index I've got in my list of 30 columns. So to do that, I'd plug them straight into here. Now you've got to be careful with this component I've found, because you really need to know what type of the data it is. So to make sure I'm talking about integers only, I'm going to make these into integers. Just pass them both through integer, otherwise it tries to compare integers to numbers and that's not going to work. So the set that I'm operating on is, and I'll flatten this, is all the index numbers of the panel centroids, and the member I'm searching for is which column it belongs to. So what this is telling me is, and if I just simplify this, it's telling me, and I'll put a panel up here just to show what it's doing. It's saying the first column, there's no panels. Column number 1, which is this one here, has one panel associated with it, which is this one. Column number 2, which is this column here, has two panels, panel 1 and 4, which is that one and that one, associated with it. So you can see that it knows how many panels are associated with each column. And you can probably obviously tell from there, it's pretty easy to work out the amount of load, because what I can do is I can just go to surface and area, work out the area of each of the small panels. And I'm going to multiply that Now I'm just going to add a third number to multiply it with. I'm going to set up a little panel. I'll call this load. And I'll call it load in kilonewtons. Whoops. And I'll say just 1 kPa for the moment. It's going to be a lot more than that. But if it's 1, you can see the results pretty quickly. So the area times your load of 1, called a kilonewton, I meant to be kPa. 1 kPa, and then I'm going to multiply it, because it'll be in millimeters. I'm going to multiply it by 0.001231. So that should give me, let's just have a look with this panel, 7.5 kilonewtons per panel. Now they're all the same here, but if you set up this structure with different grids, obviously they're all going to be different, but this just shows you you can see the results and make sure it makes sense before doing funny numbers, regular numbers. So if I go to set, I get this list of loads per panel, and then I plug in this the index numbers. Now don't worry that I've got different numbers in my lists. Ordinarily that's a bit of a worry, but I'm going to flatten this. I've got 124 items, and you can see that this list, this index number goes up to about 124. So I won't go into that right now, but whenever I use it's really important when you use list item or member index, just think carefully about how many items are in your list and how your index is related to that list and whether they're in the right ranges. Just delete that panel. So I know this is right because I've done this before, but sometimes you have to think that through. Right, so next step is I've got all my loads now for each of these panels. So as I said before, actually I'll recreate that panel. For panel 0 I've got nothing. For panel 1 I've got 7.5 kilonewtons, or for column 1 I should say. So that's that panel there. For column 2 I've got 2 lots of 7.5. I've got that one and that one. So our next step is I just want to add those together. So mass addition, and you can see again for column 0 I've got nothing, column 1 I've got 7.5, column 2, which is this one, I've got the addition of both of those, which is 15. So that makes sense. So I want to see the result of this load rundown, the next step. So I'm going to use tag, except I want to use a bit better tag than the simple one, so I'm going to use this 3D tag. I know the text that I want in the tag. The location, I'm going to get that from previous information, which was the original points, the list of 30 points that I had. But I just want to offset it a little bit because I don't want it stuck right under the column. So I'll just get a vector here. Whoops, that's not a vector. Vector. And I'll just set this to, actually I'll just make a little panel here. 200 mil away from the column, just so I can see the result in the X and the Y direction. And that's where I want my tag. Turn those points off. Now it's really tiny, probably size 1, yeah, so I'll set that to, I don't know, 500. Let's see how big that is. Okay, that's too big, and also I need to flatten this. There we go. That's not too bad, I might leave it that size. So now I can straight away see I've got 7.5 kilonewtons there, 15, 7.5. I've got 30 here, does that make sense? So I've got 7.5 times 1, 2, 3, 4. So that's correct. Yeah, so they all should be matching how many panels are associated with them. And I might just turn off some of these centroid. Oops, I'll leave that one on. Actually no, I'll hide that one and put the surfaces on. And I need to get rid of these. There we go. There we are. So that's load per column in a very basic form. Now the reason I said it was a good method before is this divide component is what we can do is instead of splitting it up into 2 by 2, you can make this as whatever number you want. So it almost becomes a finite element analysis. If I made that 10, I can have some tiny little segments and the result's still the same. So I can have columns wherever I want, all over the place, not in a regular grid, and it's going to figure out where the load's going to go, assuming it's all regular. So this video has already gone pretty long. I'm going to leave it there for today, but obviously it's pretty easy to keep going with this demo. The next couple of things we could do is put the facade loads on. That's pretty easy. I've worked out a way to do that, which I might do in a further video. And also we can specify different loads for different panels. So you'd have a concrete floor, a steel frame floor, or a roof panel, for example, and plug those different values in for the different areas. And obviously you can also create a better grid, or where every grid line is variable and all that sort of stuff. So but I'll leave it there for today. Thanks for watching this structured parametrics video. Leave a like or subscribe if you found this useful, and we'll see you in the next one.